I'm going to now talk through making an addition to the SCION model, and we're going to use the model to input a pulse of CO2 and show you how this is done. So we've got MATLAB console, we've got the SCION front end, initialize file, and we've got the SCION equations. Now, before we make any modifications, I'm going to make a baseline run. So baseline is SCION initialize of -1. Now this just sets up a run that we can compare to, so we can make sure that our new run is actually doing something. So here we go. That's a default run of the model of version 1.1.6, and we can keep that for later. Even if we delete the figure, we've still got all of the data in there. So now we're going to look at making some additions. Now, if we want to add CO2 to the model, we need to go and find the carbon reservoir and put something into it. So dy3 here, carbon dioxide, this is atmosphere ocean carbon. We're going to add a new flux. So we're going to call it CO2_pulse. Okay, so there it is. Now we need to define the size of this. So typically we could do this along with all of our other fluxes here. So let's call this CO2 pulse. Now, the simplest thing we could do is just make this whatever we want, so in moles per year. So typically most things carbon related are on the order of teramoles, so 1e12 moles per year. Now this would just add a teramole of carbon into the atmosphere at every model step, but this would probably lead the model to explode. But technically this will work. Now one thing we haven't done here is we've added the CO2 pulse as carbon. We haven't added it to the isotope calculation. So if we're going to add carbon into the system, we need to make sure that has a corresponding isotope value. Otherwise, we're not going to conserve the isotopes. So delta value times A, we're going to add it on here, plus CO2 pulse. We're going to give it an isotopic composition. So let's call that delta13C underscore pulse. We also need to define what that is. Now I'm going to put it up here with my pulse, so it's all nice and tidy. And let's make this -5, so the mantle value. So we could just run this to see what happens. Might be a nice example of the model crashing. So let's not call this baseline, let's call this exp1. Okay, so the model isn't crashing, it is running. And here is our result. So compared to the baseline model here, you can see that our new version here has substantially more atmospheric CO2. So CO2 doesn't come anywhere near present day, it's higher all the way through. Now this makes sense because we've added a substantial additional source of carbon to the model. Of course, it's kind of unrealistic. We're no longer meeting the terms that the model was defined around about the present day flux. So it's kind of meaningless as an experiment, but it shows that this is working in the model world. Now, what we actually want to do here is we want to add a realistic looking pulse. So instead of adding a static number, we're going to give this a time frame. Now the best way to do this is by using the interp command, as is used with the forcings. So we can take this size, we can use interp1. Now this function in MATLAB requires three things. It requires a time vector, a y value, so the actual CO2 value, and then the reference for that time vector. So that will be tgeol, so it will look at the time in geological time. We need to start this when the model starts, so -600, and then we need to decide when our pulse is going to be. So let's make this something recognizable. So how about the Permian Triassic? We know we have a big CO2 pulse there that's not currently included in the model. So we're going to go for -600, 252, 0. So these are the key tie points that we want. This is the beginning of the model, the end of the model, and then the time we want this to happen-ish. So this is just a guess. Now, we need to define something here that looks a bit like a top hat. So there's a few ways you can define this function. You can make a nice sigmoid, you can make a step up and step down in a curved way, or you could do a simple top hat. So that's the thing that we're going to do here, because it's easiest to define. So we'll do -600, -252, -252 again, -251, -251. Now, if we make this -252.1 and this -251.1, what we have here is a flux that, and then we do our size of our flux. So nothing, nothing, 1, 1, nothing, nothing. Now, what this means now is that we're going to get a flux that begins at 0 at 600. It stays at 0 all the way to -252.1. At -252 exactly, it comes up to 1. at minus 251.1, so 0.9 million years later, it's still at 1, and then when it gets to 1 million years later, it's gone back to 0, and then 0 for the rest of the model run. So we can easily check what this looks like if we want to, and it's worthwhile doing this kind of thing. So we can define our t-grid here. So let's say tgeol is a grid from minus 600 in 0.1 million years to 0. We can now paste in this, so we'll call this CO2 pulse. Copy it from here, paste it into there. We've now got tgeol and CO2 pulse, so I can now just ask for a plot of tgeol CO2 pulse, and this is what we've created. So it's 0 for almost all of time, and then just here where we want it, or where we've decided, it goes up to 1 times 10 to the 12, and then it comes back down. So this is a very simple way to put things into a model, a nice step up, step down. If you want to make this look a little bit more curved, you could use something like the sigmoid function or the normal PDF, normal distribution. So that way you could make this function look more curve-like, or you could put spikes in it, or do anything else that you like. But we'll stick with this because this is simple. So let's now run the model. EXP, let's call this EXP2 now, because we've already got our baseline at EXP1. So here's our output, and then we can go and look where our CO2 pulse is. So things we might expect to see this in is, of course, the atmospheric CO2 and things like the fluxes. So we can see here at 250, look, we've got a tiny little pulse of CO2. We've got a little bump in the surface temperature, and we've got a little bit of a response in things like the weathering. So this hasn't done very much to the model. Now this makes sense because this is actually relatively small. If we're talking about the Siberian traps, we might use numbers a bit more like 8 teramoles per year. Maybe we wouldn't use it for 900 kiloyears, but let's just see what this does as an example. So let's make experiment 3. And we now have a much bigger response. So that CO2 coming in has driven a large increase in atmospheric CO2 to 5,000 ppm. A global average surface temperature increase of about 2 or 3 degrees. So this model has a fairly low climate sensitivity because of the emulator, which is based on the foam model. So we don't get huge shifts in temperature because we're only doubling CO2 once, so we're only getting 2 or 3 degrees. We also see a response in carbon isotopes. So we've got initial negative excursion because of the volcanic CO2 being more negatively fractionated. But then we have a positive productivity response that brings us back to positive. So you'll see here we're not really doing the full geological record. We don't have a mass extinction or anything crazy like that. But if we were to put in larger and larger amounts of CO2, we would see larger and larger effects. So this is now getting beyond the amount of CO2 you probably would have expect to see in the Siberian traps. But just as an example, actually this is now an example of the model crashing. So this is actually a useful crash. Key upper index, it cannot find a part of the emulator that will work for this high level of CO2, and that's because we've put a rather insane number here. So let's make this a little bit smaller but less insane, just to see if we can get a model that didn't crash. Okay, looks like it's made it this time. But you can see we now have fairly extreme levels of CO2. So we're getting up to 10,000 ppm. And we're now getting big temperature responses. So we're getting 5 or 6 degrees of global warming. Carbon isotopes, a slightly bigger response, 2 per mil back and forward. Still not as huge as you might expect from the geological record, but then we don't have all of the extinction and the Planck crisis and everything else that might happen during this event. You can see we have a weathering response visible in the strontium isotopes and a few other interesting things happening in the model. So that's the basics of putting in a CO2 pulse. Now, I'll quickly also explore the other kind of pulse that you might want to put into the model. Obviously, there are lots of things that you can try, but another popular thing is to put in pulses of phosphorus. So we can make our CO2 pulse here 0 by just taking this line, making a new line, and making it 0. So commenting in and out, very useful. Now we've got no CO2 pulse, so why don't we instead make a P pulse? So this is exactly the same. We're going to take P pulse. Now phosphorus fluxes are typically more in the order of 10 to the 10 moles per year, so let's make this 2E10. For simplicity, we'll just run it on the same time frame, and we will add this into our marine phosphorus reservoir. There's no phosphorus isotopes in the model. There are no stable isotopes of phosphorus. Well, there's one, so we're not going to have to worry about that. And that should now put in our P pulse. So if I now run experiment 4, what we should see is a different model response, because instead of putting in CO2, we're putting in phosphorus. But we're still doing it 250 million years ago. So the key things we're looking for now are marine P. So you see we have a big P response. We also have a big N response. This is because now there is the invitation for the model nitrogen fixers to fix more nitrogen. We get a big response in F org, so we've got a lot of carbon burial. We've also got pyrite burial. We've got a positive carbon isotope excursion, which you might expect from more phosphorus. We're making a little bit more oxygen. Because we're making more oxygen, we're doing more oxidative weathering, so we're actually net producing CO2. So we start to draw down a bit of CO2 with our productivity and carbon burial, but quickly we increase atmospheric O2 and we actually oxidize more carbon, and we actually get a positive CO2 and temperature response. And that's probably all of the interesting stuff. You can see that there's our carbon burial has gone up quite a lot, and weathering has gone down to compensate. So that's everything. So you could put a lot of different pulses of a lot of different things into the model using these basic frameworks. I hope that was useful. A quick further note on the P pulse in the model is that I mentioned that oxidative weathering increases because oxygen increases, but actually if you zoom into this, although oxidative weathering stays higher relative to everything else, there is still an overall decrease in oxidative weathering. What is actually driving this increase in CO2 is, so it's not just that we have lots of carbon oxidation because we have more O2. That is contributing to it a little bit, but actually one of the key contributions here is this decline in terrestrial biosphere. So as oxygen concentration increases, we do get a bit more oxidative weathering relative to what we would have otherwise, but we also limit the land plants through more fires and more photorespiration. So we reduce the terrestrial organic carbon burial. So this increase in CO2 we get after our initial decrease is mostly due to this more limitation of the land biosphere and less carbon drawdown on land, rather than purely from enhanced oxidative weathering.